To keep it short and sweet, I'm a fluoride salt chemist. I obviously prefer small modular reactors and molten salt reactors, in particular fluoride ones. The topic of my talk today is a high temperature chemistry, okay? So this is direct and indirect benefits of molten salt reactors. I usually talk about chemistry, and I'm going to make a business case. So a brief overview of high temperature molten salt reactor conditions. I'm going to talk a little bit about heat exchangers, some direct applications. For those of you not in the chemistry or engineering community, I think they're going to be very much an eye-opener. Hydrocarbons, olefins, conjugated dienes, long-chain paraffins. Those of you in the chemistry community, you know what those are. And then my topic, inorganic chemistry. Going to talk about one that everybody knows, ammonia. And a little bit of salt reduction, which is a recent project that I took on. And then I'm going to talk about some indirect applications, which are indirect as far as industry is, but they are direct applications to molten salt reactors in particular. So let's start by talking about primary loop. That's the actual loop. That's the actual loop which has the fissile fuel in it. These are very well-established thermodynamic parameters over decades, studied theoretically and empirically under a wide range of eutectic salts. And I'm going to talk about those salts in just a second. This is about the heating range, of various iterations of molten salt reactors. And I'm going to refer to this table a couple of times. I wanted to point out a eutectic is something that you add to a salt to lower the melting point. And you want that. You want a large liquidus range. And you want to start low. A lot of work has been done over the decades to look at different eutectics. So we have sodium tetrafluoroborate combined with sodium fluoride. We have FLIBE right there with thorium tetrafluoride. We have the same thing down here, but look at the very slight difference in mole percent ratio. Now, I had to condense this dramatically from this outstanding paper written by Stanley Cantor. Here's the temperature range. They tried to keep it as close as they could. But look at the change in viscosity. And I will bring this up in just a moment as to why this is so important. 2.8 to 1.47. Makes sense. As you go up in temperature, you think you'd go down in viscosity. OK. This is a fifth order polynomial. This does not look anything like a linear curve. It goes like this. As you go up in temperature. I will explain again why that's so important. The same thing goes here. It's a third order polynomial. And now look, there is about a 2.6% change in the mole percent of lithium fluoride. And wow, not only does the polynomial order change, but look at that. So 14 to 12 and 12.59 to 7.30. These may as well be different salts. If you looked at the actual curves, it would be remarkable. Right in the middle, for example, of this one, it dips down to 7.3, right around 600. And then bounces back up to 11 and back down to 7.3. And I will go into the reasons why that is so important. This would dramatically affect the geometry and the pore size and just about everything you could possibly think of with respect to a heat exchanger. Now, let me stop everybody for a second and let's think about this. I'm a chemist and I want to make a cogent business case for you guys as well as for industry and investors as well as to why this is a great business investment. Nobody's actually ever considered, to the best of my knowledge, and 4 people at this great conference, Jonathan Hintz, Fred Moore, of course Simon Irish, and Mike Kolodner, brought up the fact that MSRs or SMRs in general are great thermal platforms, and that's true. But to the best of my knowledge, nobody at all has addressed the very, very different geometries and materials considerations there are going to be if you want to go make a lot of money by just doing chemistry. In other words, using an SMR or a molten salt reactor as a purely thermal platform, not producing 1 kilowatt hour. Nobody's talked about that. And the fact that these viscosities change so dramatically, and a choice of salt is incredibly important, right? Look at where we are here with sodium tetrafluoroboride. Wow. Wow. So again, let's talk about the secondary loop. The secondary loop is what you most likely are going to actually use to contact heat exchangers, right? Now, we all talk about turbines because our primary focus for many years has been, let's go make electricity. Well, I think you can make a lot more money just using this as a high temperature chemistry platform. But these considerations, nevertheless, have to be seriously thought out. And as you can see in the back here, I have the MSFR. This is a CAD drawing done by an Italian group in Europe. So this is, as I think was mentioned during the conference yesterday, this is what they're moving forward with in Europe. If we have a heat exchanger, these pore sizes, these curves, these radii of every single surface in your heat exchanger is going to matter a lot in terms of the eutectic and in terms of the heat transfer. Because what do we want to do? We want to maximize the heat transfer to our, for example, a resin bed, right? A resin bed is what ExxonMobil basically uses to make one of the highest revenue value add molecular streams, way more money per liter than gasoline. And so you need to think about those chemistries because guess what? That chemistry occurs at 300 Celsius. So let's talk a little bit about catalytic cracking. It's a fancy word. It basically says take a long, between 8 and 12 carbon long chain of a hydrocarbon, quite often it's naphtha, light or heavy naphtha, and break it down. Okay? Break it down and add what are called double bonds. These are the top 10 ethylene complexes, and look at the numbers. I mean, they're in the millions per year. Okay, we've got 3 of them here in the United States, but the bulk of this top 10 is outside the United States. Why does this matter? Catalytic cracking gives us the basic building blocks for all of the plastics in this room. The plastic in the pointer, the plastic, I mean, that's it. That's it. So 51% of the global naphtha production supply, 653 million metric tons, is used for cracking down into ethylene, and that's expected to rise, look at that number, 100 million metric tons by 2025. So let's think about this. So decane 10, right, long, considered part of the naphtha mix, and naphtha is a mixture. You break this down catalytically, but you do it at 400 Celsius. And you break it down into the constituents that I was just talking about, right? Propene will get you HDPE, right? High density propylene, and low density LDPE, right? Those little numbers on the bottom of your water bottle and stuff. Ethylene, same thing. Polyethylene. Fractional distillation, okay? This is the process by which you take crude oil here, you heat it to, again, 450 Celsius. I do prefer molten salt reactors. SMRs can't hit those temperatures. All fractional distillation on the planet is done this way. And up to 50% of the total energy of your OPEX is energy to get it up to this temperature and at these volumes. What is this doing? Crude oil comes in, you fractionate it out, your highest, lowest molecular weight fractions come out on the top. Those are your light gases, butane, pentane then, and then hexanes, and then all the way down to gas oils, MDO, bunker fuel. Well, those are used by almost 100% of the fleets, the shipping fleets, container ships on the planet. And every single, I don't care which one you name, they all do it the same way. They all need 450 and above Celsius. My favorite, inorganics. Let's start with ammonia. This process is over 100 years old. Fritz Haber initially developed it. Over 450 million metric tons per year are produced. That consumes about 2% of the world's energy production, and there's the reference right there. Now let's look at this for a second. Let's look at this curve just briefly. You would think that you would want to be up here. Wow, 80+% ammonia production at only 200 Celsius and about 180 ATM. The answer is, it's a trick question. That makes sense until you look at the equilibria, okay? You're going to get about a teaspoon per day if you do it like that, okay? So where's the sweet spot for the industry? It's about 500 and about 250 right there. And then you're talking about industrial level production, okay? But again, that's 500 Celsius, right? 2% of the world's energy production is going into ammonia. That is a lot. That is a lot. This is a kind of a favorite of mine. I've been kind of noodling with this over the past couple of months. It's a much smaller market, but it's concrete recycling. We're actually fourth. The United States is fourth in the world in terms of concrete production. Now, in many cases, you can make the argument that it's simply not a cost-benefit analysis, but where I'm from in New York, it sure as heck makes sense. You got $15 per cubic yard in the New York metropolitan area of the sand, which constitutes about 1/3 of all concrete made. So I've already made an easy argument. I don't display it here, but I've already made an easy argument for recycling, at least in the metropolitan New York area. And since nobody's done it on industrial scale, I can't even give you numbers, but I could imagine it's pretty large because over almost 4 billion metric tons worldwide was produced in 2012. That's a lot. So there's no known chemistry to drive this reaction backwards, okay? I'm estimating from my preliminary work that it's going to be around 400 to 500. I don't think I can get it any lower. So again, I need a thermal platform that's going to make business sense in order to make this happen on industrial scale. And in order to recycle it, I'm going to need something to do with that carbon dioxide rather than release it into the air or into the oceans. But at these temperatures, I can have another bit of chemistry on the side to take care of it. Cleverly, use it as a reagent and not sequester it, not bury it into the ground. I think that's a terrible idea because I'm a chemist. Again, inorganics. Okay, so I'm going to jump back very quickly into molten salt chemistry. A previous talk that I just gave actually in Washington, D.C., we talk about proliferation, and we talk about measures against proliferation with molten salt reactors. A very intelligent colleague of mine basically said, it's a political argument. Anybody with enough will and enough money, I don't care what type of reactor you use, if they have enough will and enough money to write checks, they're going to do something bad. Okay? However, as chemists and physicists, and David provided some excellent examples yesterday, I believe we can thwart that, and I believe we can do that very effectively. And let me just give you a little bit of information here. Iodine-129 and iodine-131 are the primary iodines that come off of a molten salt reactor. Iodine-131 decays in 8.05 days, so I really don't need to worry about that. Iodine-129 decays in 16 million years, so I think I can handle that, maybe even without a hot cell. Molten salt reactors, it's well known in the community that they need constant fluorination, right? So as a chemist, what is on the left-hand side has to equal up with what's on the right-hand side. So in that case, you're going to run at a fluorine deficit. Why not take some of the products, fluorinate them, and bring them back into the reactor, because you're going to keep needing fluorine. Why do I mention this? A couple of reasons. Iodine's going to be a little tricky. Okay, that's fine. But if you whack it with a neutron, which there's lots of neutron flux around, you're going to make xenon-130, an incredibly valuable isotope of xenon. Well, look at what you can do to it. You can make a xenon difluoride and all the way up to xenon hexafluoride. Again, a great fluorinating agent, easy to handle, easy to transport. and decomposes quite readily when you subject it to injection into a molten salt reactor. It's at 300 Celsius and about 20 ATM. So again, high temperature chemistry, easily done, actually makes things nice and easy to handle because you can, I put the N there because hydrofluoric acid can actually readily dissolve in xenon difluoride. So, and this N, by my calculations, is somewhere around 3 or 4, so that's great. 3 to 4 moles of HF per mole of xenon difluoride. That's pretty great. So you have increased safety. You have monitoring because, like I said, left side of the equation, right side of the equation, all have to add up. This also has tremendous importance in the semiconductor industry. They need fluorinating agents. Well, how neat would that be to go make it over there and then sell it over there? So, and of course, the MSR industry, and as I pointed out, if you add this stuff up, I think you have a relatively straightforward and near real-time way of monitoring whether or not somebody's going to be skimming off, any salts, and if they do, how much is gone. It is tricky, I agree, but I have full confidence that the scientists of today and tomorrow can pretty easily figure out with some simple tips and tricks. I think I've already figured it out, but again, I mean, there's no I in team, right? I mean, this would be a team effort. So in conclusion, I mentioned 3 well-known chemistries. That's over $2 trillion a year. The United States does about $200 billion a year alone in fractional distillation. That's impressive, just for the United States. Okay? I have not found any concerted efforts to handle heat exchange material science issues, right? With those dramatic differences in density that I pointed out for eutectics for a secondary loop, those have to be addressed. Those have to be addressed, and I think we can very competently address those, but there are lots of material science, there are lots of fluid mechanic and thermodynamics issues. You don't want cold spots, right? You don't want those salts to cake up somewhere, So, like I said, only 3 processes. So the Haber-Bosch for ammonia, catalytic cracking for naphtha, and fractional distillation. There are hundreds of high temperature. I didn't even go into OPM xylene, which has been pushed by ExxonMobil, and they make a lot of money on that. They have resin beds. They use Lewis acid catalyst. Our group at Stony Brook University actually focused on a variance of this type of a Lewis acid catalyst to effect that chemistry. But again, 400 Celsius. And so like I said before, in some cases, over 50% of industry-specific costs are dedicated to heat. That's incredible. That's incredible. So why not think about SMRs and molten salt reactors as a partner to the petroleum industry, to the ammonia industry, and derivatives thereof, right? I mean, I mentioned 3. There are hundreds. So there you go.